Hey, hello, ib1 higher level students. Next video lesson related with relativity with our optional material. Last time we're talking about time dilation and length conduction. I hope you remember this part of the material. So as at the beginning, in the form of a revision, I hope that you know what the Lorentz factor is a mathematical formula which compares frame of reference which is stationary with frame of reference which is moving due to the stationary observer, and of course mathematically it's written as 1 over the square root of 1 minus v squared divided by c squared. Of course, the best is if v, speed of the object, is expressed as as a fraction of speed of light. Okay. So we are also talking about proper time, proper length. So and about time dilation and length conduction. So what in general, what is length? Length is a proper length divided by Lorentz factor, and proper length is length measured by observer who is stationary due to the measured object. And in the case of time, time is always product of Lorentz factor and proper time. So what the proper time is? Proper time is the time measured by observer for whom the beginning of and end of the event takes place at the same point of space. So for one whose clock doesn't move. Okay, and we've calculated some examples from past papers. And I've presented an example with runner. If you have a runner who runs from start to finish, and let's name it R runner, and runner has own clock, and which is the runner is observed by fan F, which has also a clock. So for whom, which observer, runner or fan, measures a proper time? If an event is the run from start to finish line, then the clock which doesn't move due to the observer is runner's clock. A runner has always his clock, let's say 20 centimeters at the front of his nose. So for him, the clock is always at the same position. So runner measures proper time of this run. Fan measures time which is not proper. But what with proper length? When a runner runs, for him, start line is changing position during the run, and finish line also changes position during the run. So a runner doesn't measure proper length. For fan, start and finish lines are always at the same positions at space. So fan measures proper length. Is it clear? So again, in this simple example, a runner measures proper time, fan measures proper length. Okay, and today I'm going to talk about one experiment and second thought experiment. First is known as a muon experiment, and this is something which confirms special theory of relativity, which confirms the existence of phenomena time dilation and length conduction. So you can write a topic, the muon experiment, and the twin paradox. Okay, so we'll be talking about two things, muon experiment and twin paradox. Okay, I hope that you are prepared to the lesson. You have a notebook, pen, Socos is not necessary today. A calculator will be calculating Lorentz factor, length conduction, time dilation, and eventually ruler. Okay? So write point number 1, the muon experiment. Okay, yes, I know we didn't do nuclear physics, so probably you don't know what the muon is. Muon is a particle, an elementary particle, which has no internal structure like electron, and basically it's very, very, very similar to the electron. It's something like heavier version of electron. Okay, today is important is that muon is an elementary particle. Okay, so you can write somewhere that muon is an elementary particle. Okay, and what is also important, scientists measured something like which is known as a half-life of muon. Muons decay, and parameter which describes what is the rate of decay or how fast muons decay is a half-life. Half-life is time after which half of the muons in the sample decay. And scientists measured half-life of muon to be around 2.2 times 10 to the power of minus 6 of seconds. Remember, this lifetime is measured in laboratory, where muons are addressed. Okay, so it's very, very important in laboratory, where muons are addressed. Okay, and again, today you don't need to know what the half-life is. You can imagine that this is something similar to lifetime of muons. It's not the same, but something similar to lifetime of muons. Oh, maybe will be better if I tell you that after half-life, the probability that muon will decay is exactly 50%. So if time is shorter than half-life, the probability that muon exists is bigger than it decays, and when time is longer than half-life, for a single muon, that probability that it decays is bigger than it still exists. Okay, so this is something like a lifetime. Okay, and muons are also created in our atmosphere around 10 kilometers above the Earth's surface by cosmic rays from the sun. Okay, so let's imagine that this is the Earth and this is height of 10 kilometers. Okay, and cosmic rays from the sun at height of 10 kilometers create muons. Okay, and what is important here? Important here is that these muons created in the atmosphere around 10 kilometers above the Earth's surface, these muons travel with high speed. Speed of these muons is around 99% of speed of light, so this is 0.99 c. Okay, so let's look. We know that half-life of muons is 2 times 10 to the power of minus 6 seconds, and we know that muons created around 10 kilometers above the Earth's above Earth's surface travel with speed of 0.99 c. Okay, and what is important fact? The fact is that muons are detected on the Earth's surface. Not all muons created in the atmosphere, but some muons are detected, okay, by detectors on the Earth's surface, which means that the muons which are created 10 kilometers above Earth's surface should travel distance 10 kilometers before they will be decayed. Okay, so let's look. Let's first calculate what time is needed to travel distance of 10 kilometers by particle which travels with speed 0.99 c. So let's calculate time needed to travel 10 kilometers with speed which is 99% of speed of light. Okay, this is your first activity. Please do this. When you will be ready, turn the video back. I hope that you did this. Speed is distance over time. Time is distance over speed. 10 kilometers is 10 to the power of 4 of meters. Speed is 0.99 times 3 times 10 to the power of 8, because this is speed of light, all in standard units. I'm using my new calculator. So this is 10 to the power of 4 divided by 0.99 times 3 times 10 to the power of 8 in standard units is 3.37 times 10 to the power of minus 5 of seconds. So let's look. This is time needed to travel 10 kilometers. This time is much more longer than lifetime of muon. Oh, we can do another. Let's calculate maybe what distance is traveled by particle traveling with speed 0.99 c in a time of 2.0 times 10 to the power of minus 6 seconds. So find this. Find the distance traveled in time of 2.2 times 10 to the power of minus 6 seconds with speed 99% of speed of light. Okay, so your second activity, please stop video. You have 3 minutes. Please do this. Distance is speed times time. So this is 3 times 10 to the power of 8 times 2.2 times 10 to the power of minus 6, which is, I'm going to use calculator, 3 times 10 to the power of 8 times 2.2 times 10 to the power of minus 6. Enter 660 meters only. Okay, which is, let's look, which is less than 10 kilometers. Okay, so normally, by using standard classical mechanics, if muon, a particle, has a half-life of 2.2 times 10 to the power of minus 6 seconds, so in average, this muon should travel only 660 of meters, so it should be not detected at the surface of the Earth, because to be detected, it should travel 10 kilometers, not 660 meters. Let's look, this is around 15 times less. Okay? So classical mechanics doesn't work with this example. So let's use relativity. Your next task here is to calculate Lorentz factor for speed 0.99 c. Okay? So let's solve this problem by using relativity. So next, find Lorentz factor for speed, which is 99% of speed of light. You have 5 minutes. It's a little bit more challenging, but if you have calculator, I hope it's not a problem. So please stop video and find Lorentz factor for particle traveling with speed of 0.99 c. Okay. I hope you did this. 1 over the root of 1 minus v squared over c squared, which is 1 over the square root of 1 minus 0.99 squared. Remember, c is crossed. Okay, I use calculator to solve this problem. 1 divided by the square root. Where is square root here? Okay, the square root of 1 minus 0.99 squared. 1 minus 0.99 to the power of 2. Execute. It is around 7.1. Exactly 7.0888. Okay, so Lorentz factor is equal 7.1. So let's look. If we have Lorentz factor of 7.1 and observer so what distance is traveled by muons, or what time is for muons frame of reference? So now, please, sorry, not in muons frame of reference. Again, we know that half-life measured in muons frame of reference is 2.2 times 10 to the power of minus 6 of seconds. Okay, so now muons are observed from the perspective of the Earth. And Earth's observer sees muons traveling with speed of 0.99 c. And what is a lifetime of muons traveling with speed of 0.99 c measured by observer who is on the Earth? we have to multiply proper time. So now I'm calculating time needed to travel, half-life. So half-life of muons measured by observer on the Earth. Okay, remember, in muons frame of reference is a correct proper time. In the Earth's perspective, the time is Lorentz factor times t0. So we have to find this. So we have to find time by multiplying Lorentz factor times half-life of muons, which is 2.2 times 10 to the power of minus 6. 2.2 times 10 to the power of minus 6, which is, let's calculate, 7.1 times 2.2 gives 1.56 times 10 to the power of minus 5 of seconds. Okay, so for observer who is on the Earth and observes traveling muon's lifetime is much longer. What does it mean? That this observer sees that muons should travel distance, which is speed 0.99 c, in time 1.56 times 10 to the power of minus 5, which is, I use calculator, times 3 times 10 to the power of 8 times 1.56 times 10 to the power of minus 5, which is 4,600 meters. Okay, so what does it mean? Let's look that in reality, by using relativistic kinematics, by using special theory of relativity, muons don't travel distance of 660 meters, but much longer, 7.1 times longer distance, which is 4,600 meters. Yes, I know, it's still not 10 kilometers, but some muons are able to get the Earth. I told you that half-life is time needed for half of the muons to be decayed. So still some muons can get the Earth and can be detected on the Earth. Okay, so this experiment called muons experiment is something like confirmation of special theory of relativity, and you must know details of this experiment and details of the reasoning, including numbers. So what is important here? That muons half-life is 2.2 times 10 to the power of minus 6 seconds measured in the laboratory in muons frame of reference. Second, that muons are also created 10 kilometers above Earth's surface by cosmic rays, and these muons created travel with speed of 0.99 c. And fact, muons are detected. And description. It's impossible because normally they should travel 660 meters, but by using special theory of relativity and Lorentz factor, they can travel much longer distance, and some muons can get the Earth and can be detected on the Earth. Oof, if it was too fast, please move video back, copy this with calculations, and write a kind of conclusion that, including special theory of relativity, muons can be detected, and muons, of course, are detected. So this is a kind of confirmation. Okay? So when you will be ready, please run a video forward. Next point will be about twin paradox. So a few minutes later, yes? Okay, point number 2, the twin paradox. Okay, one of my favorite thought experiments related to special theory of relativity. Okay, so let's imagine that there are two twins. Okay, one, okay, Alice, which stays on the Earth, and second, Bob, okay, which travels in quite fast, let's say, spaceship. Fast means that with significant percent of speed of light to to calculate a significant tolerance factor to check differences between age of A and B. Okay, and let's imagine that both are 20 when B, Bob, starts to travel in long journey. Is that clear? Okay, so what happens? A waits, let's say, 20 years. Okay, so here A is, let's say, 20 years old. Here A is 40 years old because was waiting Alice. She was waiting in 20 years, so let's assume that she is 40 years old. Okay, and when she is 40, Bob, okay, who was also 20 at the beginning, returns the Earth. Okay, so Bob is in spaceship and he returns. But he was in the fast-moving spaceship. Okay, so his clock, if Bob is in a fast-moving spaceship, then his clock runs completely differently than clock of Alice. How? Bob measures the proper time of the journey, so the shorter one. Remember, proper time is the shortest possible. Okay, so let's imagine that for Bob, the time of the journey measured was just 1 year. Okay, the spaceship was really fast, and time measured by Bob is just 1 year. So when Bob meets Alice after 20 years measured by Alice, he is 20 years old, and his twin Alice is 40 years old. So let's look. We have two twins, and one is 40 and second is 21. Okay, but this is not paradox. Paradox is in different place of this story. Okay, let's look. This is not a paradox because due to the theory of relativity, of course, Bob measures proper time, and always one of two twins is younger than other. 1 minute, 2 minutes, 10 minutes, but always is younger. So why Bob cannot be younger than Alice? Paradox is in completely different place. Okay, paradox is here. Let's look. Let's describe this situation from the two perspectives. One which is described, Alice. Okay, so from Alice's perspective, we have something like this. At the beginning, Alice stays on the Earth, she is 20, and Bob travels, okay, in the spaceship, and he is also 20, as I wrote here, 20 and 20. When Bob returns, Alice is, let's say, 40, is just example, and Bob is 21. Again, numbers are randomly chosen, but the fact is that Bob is younger because he measures proper time. So from the perspective of Alice, we have something like this. Is that clear? Okay, but what is the journey in the perspective of Bob? Let's look at the beginning. Okay, Bob is in fast-moving spaceship and Alice on the Earth, and both and Alice and Bob are 20 years old. So Alice 20, Bob 20. But from Bob's perspective, Bob is stationary. Okay, from Bob's perspective, if speed is constant, then in Bob's perspective, Alice moves with speed v away from the Bob. And what happens at the end? From Bob's perspective, okay, Alice returns to Bob. Okay, so from Bob's perspective, Alice measures proper time. So for Alice, times should be shorter than for Bob. Okay, and here is paradox. Who is right? Because from the perspective of Alice, Alice is older than Bob, but from the perspective of Bob, Bob is older than Alice. Okay? Please stop video, copy these two pictures, including information about this paradox. Okay? So write something that from the perspective of Alice, Bob moves, so Bob measures proper time, so Bob is younger. From the perspective of Bob, copy the picture description of situation from the perspective of Bob, and write from the perspective of Bob, Alice moves, Alice measures proper time, so Alice should be younger. Is it clear? And the paradox is who is right? Okay, this is paradox. Who is right? Which point of view is better? Because both points cannot be correct. Okay? Conclusion must be the same. Let's imagine this experiment, yes? We have meeting of Alice and Bob after 1 year or 20 years, depending on point of view, and the question is who is older, who is younger. Okay? So please copy this as a paradox and think for a moment about solution of this paradox. I give you a solution in 3 minutes. Okay? Ready? Okay, so let's look. Who is right? So let's imagine that we have a situation like here. Alice stays on the planet and Bob moves interact. Okay, so let's look. What happens with Bob at the half of the journey? Okay, Bob must turn back. So if Bob travels to the right and wants to travel to the left, he must accelerate. He must change velocity. Is it clear? So first, Bob must experience a force slowing, okay, rocket to 0 and accelerate rocket to v. So Bob must experience a force. Rockets or engine of the rocket must turn back the rocket, must slow rocket from speed of v to 0 and must accelerate in opposite direction. Is it clear? So rocket changes velocity from v to minus v, so by 2v. Okay, so when a rocket changes velocity, there must be acceleration. And this is important. Bob is not inertial observer during whole journey. Bob doesn't move with constant speed all the time. Do you remember the principles of special theory of relativity? First principle was that speed of light is the same constant in vacuum. Speed of light in vacuum is the same constant for all inertial observers. And second postulate is that laws of physics are the same for all inertial observers. So in this particular example, laws of physics of Alice, who, let's state, is stationary all the time, are not the same as laws of physics of Bob, who is accelerating, who changes velocity, who is not inertial observer. Okay? So which point of view is correct? Alice's point of view is correct, so Alice is right. Why? Because Alice is inertial observer all the time. Okay, so Bob's point of view is not right. Why? Because Bob accelerates. To meet Alice, Bob must accelerate. Of course, you can say that he can turn without reducing speed, making a kind of circular path, but it's still centripetal force, it's still a kind of force, it's still acceleration. Okay? To meet Alice, Bob must accelerate his rocket, so he is not inertial observer all the time, so he is not right. So finally, Bob is younger. Alice is right. Alice stays on the Earth and her point of view is correct. Is it clear? You can ask, so what is wrong? Because the solution like Bob accelerates, so he is not right, is not full solution. Of course, you're right. I know better solution. I know mathematics of this phenomenon, but this is not special theory of relativity, but general theory of relativity. And this is something where special theory of relativity doesn't work, and we must use more complex, more complicated theory called general theory of relativity, of course also described by Einstein. And I will be talking about this during a course of general theory of relativity, so in 2, 3, maybe 4 lessons. At this moment, you must trust me that there is a description of this situation and a solving of problem, not in easy way, not in way like here. Bob accelerates, so he is not inertial, so he is not right, because we are talking about special theory of relativity. At this moment, we must finish the problem of solution of twin paradox now, yeah, in this place. Because you are not too advanced in relativity to solve this, to talk about general theory of relativity. So, conclusion, Alice's point of view is correct, because Alice is always, during whole journey of Bob, Alice is inertial observer all the time, so her point of view is correct, her description by using special theory of relativity is correct. Bob's point of view is not good, Bob is not right, because Bob is not inertial observer during whole journey. Bob must accelerate to meet Alice. If Bob accelerates, he cannot be inertial observer, so his description by special theory of relativity is not correct. So finally, Alice is right. Oof, I hope that you've made notes. Please watch this video again and again to understand this. It's a difficult problem, but nice. In one hand it's difficult, but in other hand it's fascinating. So please make a notes about muons experiment, like confirmation of special theory of relativity, and about thought experiment called twin paradox, where the paradox is not that one of the twin is younger or older than other, but who is right, which point of view is better, and describe this by using words inertial or non-inertial observers. Oof. So thank you for watching. Please again make a notes. Any questions, comments, write as a post in Google Classroom. Thank you for watching. Stay at home and see you. Bye.